So I'm going to talk about winds from the accretion flow in active galaxies and binaries. I have learnt lots about winds and physics of winds and physics of atomic processes from many people, but I'd like to especially give a name check to Ryota Tamaru, who's done a lot of the work that I'm going to show. So why do we care? We know that we see winds from active galaxies. We see absorption lines that are blue shifted. In particular, we see in the X-rays some ultra-fast outflows. Many of these, well, by definition, the ultra-fast outflows are more than 5% of the speed of light. So they carry a lot of kinetic power. But they're also quite broad. So when we're thinking about atomic physics and understanding atomic data errors, that's not a place it's going to be important. They're very high ionization, so we see them in ion 25, 26. These are things we hopefully understand quite well, though being at this meeting has made me worry. But these are the ones these are the winds that carry lots of power, kinetic energy. These are the ones that do AGN feedback. So understanding them would be a great step forward. But we also know that we see lots more winds in AGN as well. We see different ionization states, different velocities. This amazing spectrum, I think Mike Novak showed it earlier, much smaller velocity, but much smaller ionization parameter, and just lines everywhere in that soft X-ray band. These in X-ray astronomy are called the warm absorbers. They're at small velocities, so they don't carry much kinetic power, but they actually carry a lot of mass, that they are sculpting the mass that's available to accrete onto the AGN. So they're very important in terms of determining the AGN duty cycle. We don't know the driving mechanism for either of these, so we can't predict their kinetic power or the amount of mass they carry. But we also see winds in galactic binaries as well. And these are very high ionization, so mainly hydrogen-like and helium-like ion that we see them in. So that's kind of like those ultra-fast outflows in AGN. But their velocities are really quite small, more like the warm absorbers in AGN. So here in binaries, we've got nice data. These are winds features that are smallish blue shifts, smallish widths and narrow features. So these are things we can use to understand the wind dynamics. So we can try and look at these and understand how they're launched, and then think of, are they the counterpart to the warm absorbers in AGN, or are they the counterpart to the ultrafast outflows, or are they something else entirely? So let's think about how those winds might be launched. What's the physical launch mechanisms we can do? Well, these are low mass X-ray binaries. So first off, we're not looking at the stellar wind, which is important in the high mass X-ray binaries. We really are looking at a wind that's from the accretion flow. And there's only a few mechanisms to drive a wind. These are X-ray hot, so the X-rays can shine onto the surface of the disk, make it hot, and then the hot gas expands. Thermal pressure is driven by the pressure gradient. Those are thermal winds. Obviously, if your source is Eddington and above, then radiation pressure is very important, and that can drive wind. But radiation pressure on electron scattering is only the smallest possible coupling you can have. If you're UV bright, you can have UV line driving, and that's a much bigger cross section. Or of course, you can always have magnetic fields. But generally, we don't understand much about magnetic fields, and so those are difficult to constrain. In the binaries, we're looking at things that are X-ray bright, so thankfully, we don't have to worry about UV line driving or anything like that. We are often looking at things that are quite bright. Often they're not above Eddington, but often they're a good fraction of Eddington. So actually, radiation's going to be important in there somewhere, giving any other wind a bit of an additional push. But let's go back to those thermal winds, because this seems like such an obvious physical mechanism. It's got to work. And so when you look at the thermal wind, you've got your X-ray source, and it's shining across the whole disk. and it's going to heat the disk up to the radiation temperature, the Compton temperature. And that depends only on the spectral shape. It doesn't depend on distance, anything like that. It's just depending on the shape of the radiation. And that heats up the gas. Ooh. That heats up the gas, and so it expands. And that temperature means the gas particle velocities are going to be bigger than the escape velocity if you go out far enough away from the source. And so you power a wind. But because it's driven by heating and the radiation temperature is constant, then this wind has a more or less constant velocity. So one way to tell if it's a thermal wind or not is to say, well, if it's launched from a long way inwards of where the thermal wind can escape, then it's not a thermal wind. But then you need to know the distance. And that's kind of difficult because what we measure is ionization state. And we don't know the density and we don't know the distance. We can't break those two apart because remember, we're looking at these very high ionization states. In general, if all you're looking at is hydrogen and helium-like, you don't have a density diagnostic. But these thermal winds are actually predictive. There's no fudge parameters. They depend on the spectral shape, that's setting the heating and cooling. They depend on the luminosity, because that's how you're heating the wind, the rate of heating. They depend on Eddington fraction as well, because remember, you're using the radiation to give it an extra push. Depends on the disk size. The bigger your disk, beyond this escape radius, the bigger the wind is going to be. And it depends on the inclination angle at which you look. So let's go do it. Here's an example. Here's a black hole binary. Here's its continuum spectrum over on the left. Here's its Chandra HETGS spectrum over on the right. You can measure the radiation temperature from the spectrum. You know the orbital parameters. Well, you don't actually know them particularly well, but here's a set of orbital parameters that are kind of in the middle of where we think we are for this source. And so you can take that, you can take your spectrum, put it into a heating, cooling, and use that as input to a radiation hydrodynamics code and set it going, and there's your wind. Okay, then what you need to do is get the ion columns by using X star, and then you can compare those predicted ion columns, which are a function of inclination angle, with the measured ion columns, and you can actually get more or less ion columns that are consistent with those observations of the column you need in ion 26 and 25. So this is just showing various slices through that wind. You have to then put it into a radiation transport code as well, do Monte Carlo simulation of this, because some of these lines are resonance lines, and the scattering and emission as well as absorption. But you can do that, or rather Ryota Tomaru can do that, and then you can get these results out and you can start to compare them to the real data. And this is amazing. So it gives you at least a way of saying what's feasible to do with thermal winds. And this particular data set looks like a nice match, more or less, to the predictions of thermal winds. So let's go further, because we want to know is that are most of the winds we see like this? We want to test it on a very different kind of source. And so one of the biggest disks, remember, the bigger the disk, the bigger the thermal wind. One of the biggest disks we have is a neutron star disk accreting source called GX13+1. And this source has an amazing disk. If I was to compare it to the one we just did, that's the one we just did. Right, now we've got a big disk. So here's the big disk, And we'll do the same thing as before and do the radiation hydrocode, extract the density structure along what you think of is the line of sight, put it through X-star, get the columns, and these are the column densities you get in terms of radius along there. You're seeing there's a bit of a shift between the velocity you expect for iron 26 and iron 25. Then you put it through the radiation transport Monte Carlo code, and you now see that actually scattering is quite a bit more important. We've got much more wind. Scattering and emission in the wind is now important as well. You can also see that now the lines saturate. The K alpha lines saturate because the wind is big. So let's put those up against the data. Yeah, it's not bad. It does pretty well in terms of describing the features that we're seeing around iron, K alpha, helium-like and hydrogen-like. And that is quite impressive, because I can think of lots more physics we didn't put in, because this is a wind above a disk surface, and so there might be some sort of turbulence generated in a shear layer there. There's an accretion stream coming from the companion star that could generate you some turbulence as well. We've neglected this scattered flux, which I told you was important. We've neglected it in terms of the ionization balance and in terms of irradiation of the disk as well. And I suspect that wasn't a good plan. Nonetheless, we're getting a good-ish description. But we really want to do better. And John Miller was talking earlier about the Chandra third order data. And this source is bright enough that you can do this. You can go and get the third order data. So instead of having this kind of blurry look at 25 and 26, you can, get this 15 EV resolution, maybe on a good day with a following wind. And you look at the iron 26, and you can resolve the doublet. I reckon I can resolve that doublet, which is 21 EV. If I could see my cursor, yes, here's my cursor. I reckon that doublet is actually resolved. And why is that important? Well, it's important because these thermal winds are actually amazingly clean. Thermal winds, I said, they're kind of constant velocity. And so here's our thermal wind. I'm just taking the absorption now, just to make it very easy. And I'm going to fit it with a single Voigt profile for the doublet. And it's pretty narrow. It's fitting to a temperature that is not much more than the real temperature of the gas. And there is some radial velocity shear in this thermal wind. It's not exactly constant velocity. So it's got a velocity change across it of about 150 to 200 kilometers a second. And it's quite symmetric. So if I put that up against that Chandra third order data, it resolves me the doublet. The wind is quiet enough. The wind turbulence and shear velocity is low enough that Chandra third order should get me the doublet. And then we can compare that to a magnetic wind model. Magnetic winds are not completely unconstrained. One of the things they generically do is they tie into the disk, and then as the disk rotates, you get this kind of bead on a wire acceleration out, and that's converting azimuthal velocity to radial velocity. And so then your radial velocity is pretty much the azimuthal velocity. And there's been a lot of magnetic wind models done by Fukumura and his group, and also Ferraria and his group as well. So I'm just going to take this one as a generic model. So they make these scaled models, and the line of sight velocity, that's pretty firm. Their density profile is a free parameter, sort of, but they're pretty clear that the sort of density profile they like. And so I take their density profile, and that then predicts me an ionization profile, combine it with an ion fraction calculation for that spectral shape, and you get a prediction for the doublet iron 26 shape.
5 minutes until questions.
Okay. And here it is. Oh, green doesn't show up great. I'm hoping you can see that. So this is the predicted line you get if you say it's got to have the right blue shift to match with the data. That then sets you the density you need for your central density. Then you scale it down in the way that they want. And these have blue wings, but they're also generically quite broad. And the reason for that is, let's go back to our thermal wind model. Our thermal wind model was driven by the expansion of the gas, and the gas was getting heated to the radiation temperature, so that was a constant velocity. It's that solid black line on the plot here. And most of our iron 26 is made over a rather small range in this radial velocity. The azimuthal velocity, on the other hand, is that dashed black line. And you can see that that dashed black line has much more change over that radial range where iron 26 is going to be produced. And so that gives you a broader line. And that is noticeable. That, with CRISM resolution, is a detectable difference between the two. But then you think, well, even with third order Chandra resolution, can't I already do this? And that's what it looks like at the third order Chandra resolution. Now, I reckon I preferred the doublet being marginally resolved. So if we're choosing between that, and I think I like the narrower line profile that you get from thermal winds. So by eye, it's better, but CSTAT wants actually to fit something broader, but this is Chandra third order, and there's a lot of point-to-point scatter because of chip effects and many things that I don't understand what I'm doing with Chandra third order data. We need CRISM to go and see this. So this is basically my bottom line. Magnetic wind models predict different line profiles to thermal wind models, and we can tell the difference. Well, we need something better than Chandra without the systematics, without pushing it to the absolute limit. We can tell the difference between different wind launching mechanisms. We can get at the physics of accretion disk winds with the combination of some of these low mass X-ray binary winds and CRISM resolution and Athena. Thank you.
Great talk, Chris. Does anybody have any questions so far? Leah Corrales mentioned on Slack that regarding not finding ISM deaths in your XSpec distribution, she forgot to mention you can download and install it as an XSpec local model, and that's...
yes, that was my comment on her talk, yes.
Oh, okay, sorry. And let's see, from Richard, so it looks as the UFOs and the AGN should not be thermal winds.
That's correct. So if you then try and scale this, you're the sort of, when you scale this up to AGN, these thermal-radiative winds look a lot like the warm absorbers. Radiation pressure on dust might well be helping them along their way. Daniel Proger did some work on that quite a while ago. So these then look like they might be telling us about the physics of warm absorbers, but not about the physics of ultrafast. So then, of course, AGN feedback, the kinetic power, is the UFO. And magnetic winds would have linked the binary winds with UFOs. But if instead these are thermal winds in binaries, what are the UFOs? Well, funnily enough, my spare slides are all about UV line driving, because UV line driving isn't important in the binaries because they're so X-ray bright, but AGN have UV disk temperatures, and it's very important. But we've said as a community, but the ultrafast outflows are very high ionization, and to get UV line driving, you need UV opacity to push on. So that's low ionization, so this can't possibly work. But remember, we're not in a spherical situation, we're in a disk. We can have our low ionization material low down, close to the disk, push it, accelerate it, get it going really fast, then ionize it, and it's ionized in our line of sight, but going very fast. So then you say, well, can that work? Well, you can hang out with some radiation hydrodynamics people and then do Monte Carlo radiation line transport and figure out that there's lines of sight through a UV line driven disk wind that are very high ionization, very high velocity. So I reckon that the UV line driving could actually be part of the answer for the ultrafast outflows. I hate magnetic winds because I hate things I can't calculate.
We have one more question from Sandeep Root on Slack. Is it possible to have ultrafast winds at low inclination at about 30 degrees? If yes, are there any such cases?
So I'm hoping that the question's about an AGN wind, because we don't see much in the way of ultrafast outflows from the binaries I was talking about. This is at 48 degrees. This is a line of sight on this particular simulation, but the opening angle of the UV line-driven wind changes with things like mass and mass accretion rate and X-ray fraction. So if you absolutely needed it to be 30 degrees, I could probably get you one at 30 degrees, but this particular one is showing that a sight line of 45, 50 degrees would give you the conditions you need for very high ionization, but very fast material.